Belt. Here's our team members. Brian is our software and hardware programmer. I'm in charge of the circuit design. Dave is our belt designer. Corey is in charge of power management, and Dr. Obey is our faculty advisor. So our team is designing a belt-mounted navigation device which will guide a soldier to a programmed destination using haptic feedback. The problem that we're addressing is that the current GPS that soldiers are using today can be very distracting. If we refer to this image here, we see that the soldier is primarily focused on the GPS and not his surroundings, which could result in a possible casualty. Also at night, the current GPS illuminates, which could give away the soldier's position at night. And due to its portable function and relatively small size, it's more likely to be lost or stolen on a day-to-day operation. So we propose a haptic feedback device which will be worn around the soldier's torso. It will provide the soldier with complete hands-free navigation, and it will allow the soldier to constantly always be focused on his surroundings and not worried about the direction that he needs to go. It also has no luminosity, so there's no fear of being detected at night. Here's a list of our technical design constraints. We'll start with the digital compass, which must guide the soldier without any type of magnetic interference from any of the gear that the soldier may already be equipped with. The transmission range, for our testing purposes, we wanted to reach a maximum range of 75 yards from headquarters to the belt. Our power supply, we researched that soldiers spend anywhere from an average of 4 to 5 hours in the field at any given time, so we wanted to meet or exceed that statistic with a minimum of 5 hours. Our tactor strength, through testing, we found out that we needed to supply the tactors with at least 100 milliamps of current for them to be strong enough to be felt through the thick fabric of our belt. And also the component size in general needs to be small enough to be small and lightweight to be able to be encased within our belt. Some of the non-technical design constraints are that our first cost, since we were allocated $500, we can't exceed our budget. As far as weight, we also researched that soldiers can carry up to 150 pounds in gear. So the last thing we wanted to do is add to that weight. So we thought that if we designed our belt to be under 2 pounds, that it would be relatively non-existent to the soldier. As far as reliability, we considered reliability and ordered all our parts to have a lifespan of at least 5 years, so there's no need to replace any components before that time. For transmission, since we'll be using radio frequency, we must comply with Part 15 of FCC, Part 15 of the Rules and Regulations of Transmission. And the durability of the belt, the outer layer of the belt has to withstand the normal wear and tear that the soldier is going to face on a normal operation. Here's a block diagram of our system. We like to represent headquarters as a laptop, which will be connected with a microcontroller board, which will also have a RF transceiver on it. The RF transceiver will transmit the coordinates to our haptic belt and be received by our second RF transceiver. Our transceiver is connected to a microcontroller board, which will also have a GPS module, where the GPS module's sole purpose is to locate the current position of the user. Also connected to the microcontroller is a digital compass module, which will determine the heading of the user. Once the microcontroller receives all these inputs, it calculates and processes all the data and determines the appropriate output switch to close, which essentially will fire the appropriate tactor, which is facing the direction of the destination. The tactors are located around our belt in a clockwise manner, so 1 will be straight in front, 2 will be on our right hip, 3 will be on the rear, and 4 will be on our left hip. Our entire system is powered by a lithium-ion battery. A little bit about the components that comprise our system. We have 2 Arduino Uno microcontrollers to process and calculate our data. It was easily programmed with a C language, and it outputs 3.3 or 5 volts. It also has 14 digital I/O pins and 6 analog pins, which is more than enough to accommodate for all of our components. As I mentioned before, we'll be using 2 RF transceivers. They utilize a frequency of 433 megahertz. They have a low power consumption by offering a power down mode, so when we're not transmitting or receiving coordinates, they're not using that much of our battery. And it also has a line of sight range of 250 feet, so that exceeds our transmission range of 75 yards. And it also has a high-speed data transfer rate, so we can send and receive coordinates fairly quickly. Here's the GPS module we'll be using. It's the EM406A. It outputs an NMEA data string, which you can see right here is the typical output. As I mentioned before, its sole purpose is to locate the current position of the user. So from this string, we'll be pulling the latitude and longitude coordinates. Here's our digital compass. It's great because it has a continuous measurement mode. It's constantly updating the heading of the user. But it also features a low power consumption. So even though we're constantly measuring, it's not constantly draining our battery too much. It also will, in the end, determine which tactor is going to vibrate. And it also displays the heading. So for testing purposes, we were able to read the heading that the digital compass is displaying with an actual compass to make sure that it was an accurate read. Here's the switch we'll be using to control our tactors. It's the MAX 4678. It's a quad single pole, single throw analog switches. It contains 4 normally open switches. And we chose this switch because of its low on resistance. Since we'll only be powering our tactors with 3.3 volts, we'll be able to see maximum current to our tactors. And it operates at a range of 2 volts to 12 volts, and we'll be using the 5 volts from the Arduino to power our chip. Here are the tactors we'll be using. It's a PicoVibe 9mm. It's a vibration motor. It's a low rated voltage at only 3 volts, and it has a high rated speed. As you can see, it's encapsulated in a waterproof seal, so if our belt were to ever get saturated in any type of wetness, we wouldn't be worried about damaging our tactors. And about the motor, it uses a rotating eccentric mass, which is a weight which spins about a shaft. And because of that reason, we had to mount it to make it more stable onto the tactor pad, as you see above here. And it also protects the wiring, so when it fires, it doesn't have any danger of pulling the wires out. Here's our power supply. It's a lithium-ion battery. As you can see, it's a backpack, and it made it easily for us to mount our Arduino directly on top of it, which saves us space in our encasement. It outputs a regulated 5 and 3.3 volts, and it has a battery capacity of 2200 milliamp hours. It's lightweight and rechargeable. It also has no memory effect, so we're able to discharge and recharge our batteries many times as we need, and without seeing any type of decline in our battery capacity. In determining what type of battery capacity we needed, we used a simple equation that battery life equals the battery capacity over the load current. So we determined that our max current draw for each of our components at the operating voltage was around 300 milliamps. So solving the equation, we estimated about a 5-hour time of use that we would have operating at max current or max current draw. And since we will never be operating at max current draw, we're confident that we'll exceed our 5-hour minimum. And here's the belt design. You can see on the screen. It's also here in front of me. So we're able to place tactors in the rear of the belt as well as in the side here. The tactors are placed in between 2 of the padding material to cut down on any type of vibration noise that may occur from the motor. It's also the back and the front tactor on the clip is going to be stationary, so they will never move. But the tactors in the side are adjustable, and they can go a couple inches in both directions to accommodate different waistlines. We also were able to wire the belt with a lot of extra slack so we can do our testing without having it within our encasement. A little demo about how our system is going to operate. We have our soldier, which is going to be equipped with a haptic navigation system belt. Our headquarters will transmit the coordinates to our belt, and it will determine the direction of the destination. The greatest thing about our belt is a pick your own route. So if an obstruction were to occur, you would be faced with an obstruction, or if there was danger in the near vicinity and they needed to make their way around that danger, they could do so, and they would always be reminded of the direction of the destination, so there would be no fear of falling off track. And another unique feature of our belt is a distance indicator. So when the device is over a mile out, the time response of the tactors will be once every 10 seconds, and as the user gets closer and closer to the destination, the time response of the tactors decreases to when you're within 100 feet, it'll respond every second. And the user knows he has reached the destination because he's indicated by all 4 vibrators firing twice simultaneously. Here's some of the testing we were able to do with each of our various components, and in the following slides I'll go a little bit more into detail about each test. So here's our compass tactor test. This is a proof of concept that we can control our tactors with a heading constraint. And before I play, we're going to be representing our tactor as a LEDs for obviously video purposes. And currently we're facing northwest in the video, as you can see, so you can pay attention to the outputs here. And we set the constraint to every time there's a north, south, east, or west direction that is red, the detector would fire. So as you see it now, it's on west, it's firing. And when it removes off of west, and now it's reading northwest, and now until it goes to true north, and then it'll fire again. So this proves our concept that we can control our tactors with a heading constraint. Here's the Max 4678 is our switching unit, and we had to test, because as I mentioned previously, it has 4 normally open switches, so we had to test that we could close each individually switch, which would in the end result fire the appropriate tactor. So the trigger wires are indicated with the black tape, so we had to test each switch individually to make sure that we could close the appropriate switch with an input voltage. We also tested out that we could close 2 switches simultaneously so that we would be able to fire 2 tactors at the same time as well. Here's our transceiver test. As you can see, they're fairly close to one another, so we're transmitting and receiving data fairly close. Right now, we're transmitting a hello world string, and on the receiving end, we're receiving hello world back, but it's in a decimal format. So currently, we're working on changing this decimal format back into a character form, so it'll be easy for us to set constraints in our program. Here's a wiring diagram of what the system will be which will be encased in our system and hidden in our belt. Some of the technical challenges that we're facing to date are some transmission issues. We noticed fairly quickly that you need a clear line of sight, and we also want to reach our 75 yards of our 75-yard transmission range, so that involves us getting outside and going further and further and transmitting and receiving data. We also found out that the GPS doesn't get a reliable satellite fix without a clear line of sight to the sky, so we're not able to test it within a building or in a wooded area. We're also working on a way to securely encase our components, because the last thing we want to do is have the soldier have to make a quick jump to the ground or maybe roll over and crush the component box, and then it essentially crushes all the components and makes the belt useless. Some of the risks we're facing is that the unit coming in a little too heavy. So we're currently looking on ways that we can trim the belt down, maybe some extra padding so it can reduce the weight. And also we're facing a risk that the device may overheat, so we're currently looking into ways we can ventilate our encasement so that the device doesn't have to worry. Here's a cost breakdown of the components which comprise our system. We're currently coming in at a unit price of $350 per unit, so our budget is $500, so that gives us about $150 leeway. So if we want to upgrade any of our components or make any changes, we still have the money to do so. So as a summary, we were able to fabricate the belt as you saw the previous. We also were able to test the GPS for a fixed location with a clear line of sight to the sky. We were able to program the tactors as you saw the video before, so it proves our constraint that we will control our tactors with a heading test. We also were able to transmit and receive data at a fairly close distance, so we're working on expanding that distance. And what we plan to do is, as I mentioned, we're meeting our transmission rates. We want to get our maximum range of 75 yards, and we want to design the encasement so it's strong enough and durable enough, and also small enough to be hidden in the encasement, hidden within the belt. We want to complete the necessary source code that allows us to control all of our components all at once, simultaneously at one time. And by the next time you see us in the next design review, we hope to have, or we will have, a fully functional prototype to demo off to you. Here's a list of our references. Does anybody have any questions?